Hey y'all, today we're going to be talking about differentiability. Big word. It just basically means when can a function's derivative exist on a graph. So we've talked about this idea of what continuous means. Continuous at a point, remember, means that the left-hand limit, the right-hand limit, and the function's value at that point are all equal to each other, right? So that there is no discontinuity in any way. Then we talked about the idea of what it means to be differentiable. So we have this idea, the definition of differentiability, or to check for differentiability, we would say that we have to have three things be true. Number one, the function has to be continuous at that point. You can't take a derivative of a function that is not continuous at a point. So if you have like a jump discontinuity, you can't take the derivative of that because it's not a smooth graph. Because another way, remember, of saying derivative or differentiable is the rate or the slope at a point. If we have a discontinuity, we can't figure out a slope at that point, okay? So number one, it must be continuous at that point, okay? And then, so to just notation-wise, that means the limit exists and it's equal to the function's value at that point. In this case, I put a. The second thing is that the left-hand derivative and the right-hand derivative must be equal to each other, right? If the left and right-hand derivatives are not the same, then we have some really funky shape going on here. We got something called a corner or a cusp or something along that line, okay? And the third thing is that the derivative must exist at that point. In order for the function to have a derivative, it must exist at that point. The derivative must exist. But that basically meant that the derivative was not producing an infinity or a negative infinity. So in other words, we weren't getting any kind of vertical tangents in any way, okay? So those three things must be met. We're going to talk about now the different types of non-differentiability. So what does it look like when a function is not differentiable? Again, let's go back to continuity. We remember that when we have a jump discontinuity, right? A jump discontinuity is when the limit as x approaches some a value, some value of f of x from the left is not the same as the limit as x approaches the a value from the right. Okay, so that's a jump discontinuity. And then we have the removable discontinuity. So when we have something that looks like this, but we have a hole here, that's a removable discontinuity, and that is when the limit as x approaches a of f of x is not equal to f of a. But we have to check basically the left and right hand limits, so that would imply that the left hand limit does in fact equal the right hand limit, right? But those things do not equal f of a. So that's a removable discontinuity. And then we have our infinite discontinuity. And the infinite discontinuity is when we have a vertical asymptote, anytime we have a vertical asymptote. So that is when the limit as x approaches a from either the left or right hand side produces positive or negative infinity. Okay, so that gives you your infinite discontinuity. Again, vertical asymptote is produced there. So those are the different kinds of discontinuities. Now let's talk about the different kinds of non-differentiability. And I'm going to kind of put them up here, but we'll kind of go through them a little bit slower on the board. The first one is a corner. And the idea of a corner, the example I gave you here is kind of like an absolute value function. Absolute value function is a corner, but there's also a lot of different other types of corners. So we have to be careful with that. The idea of a corner is simply this, so I'll write this down. A corner is when the function is continuous, okay, and then the left and right hand derivatives produce different numeric values. Okay. So, and there's one exception to this, and generally we don't see it too often, But the idea is this. Okay, we have a continuous function. If the derivative on one side, let's say it's looking something like this. If I were to draw a tangent line the best I could at that point, we would see that that slope would be a value. There would be a numeric value to it. And then from this side, let's say, we would see that if I drew a tangent line on this side, it would kind of be a horizontal tangent line. So we could say that the slope from this side is 0, and the slope from this side is some negative numeric value. This is an example of a corner. So we would say essentially this, that f prime of A, if this is the point A, from the left is not equal to f prime of A from the right, and f prime of A from the left or f prime of A from the right is a numeric value or a number, okay, is a constant. Well, I don't want to say constant, but that's the idea of a corner, okay? So if the left-hand derivative does not match the right-hand derivative, generally speaking, you're going to get a corner. We'll go through the example of something that kind of contradicts that in a second, but generally speaking, it's when the one-sided derivatives are not the same. So we would say that an example of that would be the absolute value function, okay? That the left-hand and right-hand derivatives are different. The next one is called a cusp. A cusp. Well, a cusp looks very similar to a corner. Again, the function must be continuous. The function is continuous, okay? And in this case, the left and right-hand derivatives produce opposite infinities. Okay? So essentially what we're saying is that f prime of A from the left is equal to infinity, and f prime of A from the right is equal to negative infinity. Or it could be that f prime of A from the right, or sorry, from the left is negative infinity, and f prime of A from the right is positive infinity. So graphically what that looks like, looking at this first example, if I'm looking at the derivative from the left of a point A and it's going off to infinity, that means the tangent line is going vertical, but the function is increasing because the slope is positive. So we're going to have something for this example that does this. It goes up and it becomes vertical essentially. Then on the other side, the right hand, we're going to have it go up to it like that. I don't want to say up. It's actually going down because negative infinity, if I were to draw a tangent line here, we are decreasing on this side, so we would say it has a negative infinity slope, whereas on this side, it's increasing to that vertical line, so it's a positive infinity slope. Here, this slope is negative infinity. That means the function is diving downward till it hits vertical. And then on the other side, it is increasing from that point to where it's vertical. Okay? So you can see that these look very similar to corners, but they're very sharp corners. So much so that they create this like verticalness, this line, if you would, rather than a dull corner, right? That's a dull corner, and you could argue that this is a sharp corner, sure, but again, the slope here is some numeric value on both sides, where this is going vertical. This isn't necessarily going vertical. So that's the difference between a corner and a cusp. We would say that the one-sided derivatives are opposite infinities. Okay, so f prime of A is negative infinity from the left, and f prime of A from the right is positive infinity, or vice versa. But the bottom line is that they're different infinities. Okay, and so that an example of that is f of x equals x to the 2/3. If you put that in your calculator, you can see an example of a cusp. The last type, actually the second to last type, the last type is very simple. We've kind of already talked about that one. But this type is a vertical tangent. So a vertical tangent is this, that f, see, vertical tangent, okay, that f is continuous when, x equals a, let's say, okay, and the left and right-hand derivatives, are, or produce, are is fine, produce the same infinity. Okay, so let's understand that. What that's saying is that essentially f prime of a from the left is equal to f prime of a from the right. They're the same infinity, which equals plus or minus infinity. So graphically what that looks like is, if I was to graph f prime of a from the left and it's going off to positive infinity, it's going to do something like this. Positive infinity increasing. From the right, it's going to continue on in that fashion in a sense. So at this point, we would get a vertical tangent line because we're getting infinities, but because the infinities agree, this one's increasing, and then from that point, it's increasing also. Whereas in the cusp, it was increasing and then it was decreasing. So here we have a positive infinity slope, here we have a negative infinity slope. This is a cusp. A vertical tangent looks something like that. Or it could be where it's diving down to vertical and then coming out of vertical, but notice it's still decreasing. Decreasing on this side, decreasing on that side. That's what a vertical tangent might look like, okay? So we would say that f prime of a is positive or negative infinity. So because these would match, we could just simply say f prime of a is positive or negative infinity. It does not exist, the slope does not exist because it's infinity, but they do agree that they are the same types of infinity. And the last one, I'm not going to dwell on this one. An example of vertical tangent would be the cube root of x, or x to the 1/3, okay? The last type is any discontinuity. Any kind of function that is discontinuous at a would imply that the derivative does not exist at a. Even though if you look at my example here, you can see that the left-hand derivative is 0 and the right-hand derivative is 0. Okay, the derivatives match, but because it's discontinuous, it is not differentiable at that point. And so an example of this, like a classic example, is piecewise functions. Another example of this would be something like f of x equals absolute value of x over x. That function is a jump discontinuity, so it's not differentiable at 0. We could also say something like this, x plus 3 over x plus 3 times x minus 7. This is discontinuous at x equals -3, therefore it's not differentiable there. Same thing at x equals 7, it's discontinuous there, so it's not differentiable there. Okay. All right, so that is the discussion on different types of non-differentiabilities. Okay, those are the 4 different types. Let's go ahead and look at an example of this and figure out, what's the question here? Where are the following functions differentiable, and what type of problems exist where it's not differentiable? Okay, so for the first example, we have f of x equals absolute value of x minus 2 plus 3, and we want to know where this function is differentiable, which implies that we want to know where it's not differentiable. This is absolute value, so you should know how this graphs. We have a shift to the right 2 and up 3, and we have an a value of 1, so it's just the standard slope of -1 going in and 1 going out. And so we can see that here we've got that corner, but understanding why, because we would say something like this: f prime of 2 from the left is equal to -1, and f prime of 2 from the right is equal to +1. And we know that because it's a standard a value of 1. Since these do not match, we are not differentiable here. We would say, therefore f has a corner. We'll write it like this: f is not differentiable when x equals 2, and then I'll just put in parentheses, it's a corner. So here's the work for it essentially, here's the answer for it, and here's the rationale, okay? So it's not differentiable at 2, implying that it is differentiable everywhere else. There's no other place here. It is continuous, so that's not an issue, but it's the corner there. So that's number 1. We know that it's differentiable at all points except 2, if you want to write it that way. Or we could say something like this: differentiable for negative infinity less than x less than 2, and 2 less than x less than infinity. We could write it like that as well. Okay. For number 2, we have an interesting function here, and we probably should just look at the graph of this. We have the cube root of the absolute value of x. The cube root, g of x, is equal to the cube root of the absolute value of x. So that means no matter what x I plug in, I get a positive value out. Now I'm going to just do a quick sketch of this. The cube root of x should look like this, right? You should be familiar with that. If I'm taking the absolute value, then what this is saying is as I plug in negative x values, I get negative y values out because of the cube root. But in this case, as I plug in negative x values, they become positive, which means the y values become positive. The numeric values remain the same because we're only changing the sign for those negative values. So really all that does here is it flips this guy up on the other side, or it reflects it over the x-axis. So this graph is going to look something like this. Okay? Now, you might say that looks like a corner to me, or a cusp. Which one is it? How do I tell? Well, if you think of the inverse function here, some teachers call this the chill, right? Right here. If we're looking at the inverse function of the cube root of x, x cubed, we see that this tangent line is essentially horizontal, which implies that this guy is actually going vertical because it's the inverse. And so we can see that since this is going vertical on both sides, it's going to end up being a cusp. We would say that g prime of 0 from the left is equal to negative infinity, and g prime of 0 from the right is equal to positive infinity. Therefore, g is not differentiable when x equals 0, and that would be because it's a cusp, or it's called a cusp. And so we can conclude also that it's differentiable for negative infinity less than x less than 0, and 0 less than x less than infinity. So those are 2 examples of what you might see. And again, we're kind of just looking at it in terms of graphs right now because we don't fully understand how to take a derivative analytically yet. Eventually we will learn, and so we'll be able to do this a little bit more analytically in the future. What do I got here? Differentiable at all points except 0 for that one. All right. So I have moved locations. I'm no longer in front of my whiteboard. I'm on a different camera. I'm on my desktop because I think what the next concept needs is a graph that I can easily manipulate rather than using our graphing calculator. It's a little quicker and easier to see what's happening here. The idea of differentiability at a point is essentially that the function is continuous is smooth at that point. Aside from it going vertical, we don't want it to go vertical, but if the function is smooth at a point, then you will be differentiable at that point, essentially. That's the layman's way of saying it. Now we can look at this parabola, and we can see that this parabola is smooth everywhere, and it never actually goes vertical, so we could say that this parabola will be differentiable everywhere. But the way to observe that is something called local linearity. Okay, so local linearity means that if a function is differentiable at a point, then you should be able to zoom in enough to make it appear that it is a linear function within the interval that you're looking at, within that very small window or the very small interval. And so in this case, the example that I have here is y equals x squared. And so if this is truly differentiable at a specific point, I should be able to zoom in at that point and see a line, observe a line over that small window. And so as I look at x squared, I'm going to focus on when x equals 1/2. So when x equals 1/2, that's going to be right here. Now, if I zoom in at x equals 1/2, and I just zoom in, zoom in, zoom in, you might say, well, this parabola appears to be widening out. I wouldn't say it's widening out so much. We're just zooming in at a specific point. But as I zoom in and zoom in and zoom in, you can see that the curvature of this thing kind of disappears. And then if I keep zooming in and keep zooming in, we can see that this function starts appearing to be linear. Now, we already know it's not linear. We know it's a parabola when we look at the entirety of the function. But we are looking at a very small window here. In fact, we're looking at from like negative 0.48 to 0.51 or 0.52. And again, I can keep zooming in and I see a line. Okay? That's what it means to be locally linear. If I see a line through a very small window, then that function will be differentiable at that point within that window. Okay? So I'll go back to the home domain. You can see that it's not a line, but I can zoom in and see that line or make it appear to be linear. Okay? That's kind of how you can look at differentiability here. Okay? If I look at the other function here, the x minus 3 raised to the 4/5 power plus 2, well, the first thing you can see is that we do have a shift of 3 units to the right and 2 units up, so that's why we have this point here. Now, I don't necessarily know what x to the 4/5 looks like, so that's why I graphed it here. But if I were looking for whether it's differentiable at a specific point, if I came over here to, let's say, -2 and zoomed in, it would be pretty quick that you would see a line, or it would be locally linear at this x value, at x equals -2. And so therefore it's differentiable at x equals -2. But if I go back to this vertex, if you would, when x equals 3, and I zoom in here, what do we see happening? We see that the function's appearing to get steeper and steeper on both sides of that vertex. And if I keep zooming in and keep zooming in and keep zooming in, I see that it's actually going vertical here. It's actually going vertical. Keep going, keep going, keep going. And what appears to be happening is that it does appear to be looking like it's a linear function of some sort. But notice, it's a vertical line, first of all. And secondly, it's not even a line. If anything, it's a ray because it starts here and it keeps going up that way. So if I could zoom in more and more and more, it would look more and more like this ray. But because it's not linear, because it's not a line, if you would, it's not a continuous line that goes on forever throughout that entire interval or throughout this entire window, then it's not differentiable at this point. So we can say it's not differentiable when x equals 3, again, because we have a cusp. But you can see what's happening with the cusp. This thing is getting steeper and steeper and steeper till it looks like it's a vertical piece of a line, but it's not a whole line. So it's not differentiable there. Let's go ahead and take a look at maybe a different function. Let's take a look at, I don't know, our 1/3, and we'll do an absolute value function here. Absolute value, whoops, got to put it in the right place. Absolute value of x, for example, okay? And we'll graph that. So if we look at this function, we can see it's not differentiable here. But could we zoom in enough to see a line out of this? And you can see nothing's really changing. As I zoom in, zoom in, zoom in, zoom in, nothing is changing, right? And so we end up with something that is not locally linear at x equals 0 here. No matter how far I zoom in, and believe me, I'm going pretty darn far here, nothing's really changed. Another example might be, let's see if I can do this one here, x raised to the 1/3. And then I'll put a little shift there so we can see it, plus 2. And then we'll say plus 5, okay? So we can see here that it looks smooth everywhere. But as I zoom in here, no matter where I zoom in, I'm going to end up with a tangent line. Somehow I'm going to look like local linearity. The problem is that as I zoom into this particular point, I end up with a vertical line, and we know that it's not differentiable when we get vertical lines out of this. So that's another example of this. Okay. Now, talking in general, another way to look at this, an example of this would be Earth, in a sense, right? If we look at Earth from a view outside of Earth, right, a distant place, let's say from Mars or something like that, what we would see is a very small circle. And as we get closer and closer to planet Earth, we see that circle gets bigger and bigger and bigger. Well, if we go into just orbit of Earth and just take a picture from some sort of satellite, what we would see is some sort of arc for the Earth. We wouldn't see the full circle necessarily, and we wouldn't see a flat line. We would see an arc in that picture. The skyline would be an arc. Now, as we get closer and closer and closer to Earth, that arc flattens out, and as we're standing on Earth, we are really close to any point on Earth, and we look off to the horizon, we see a flat line. We see that the Earth is locally linear, if you would. So you can kind of understand local linearity through that lens. All right, so I'm going to jump back over here into my regular camera view. Hi, and we're going to go through the last problem here, the exit problem, where we have a piecewise function, h of x, and let's see what happens here. So it says identify any points where the function is not differentiable and determine f prime of x, where f prime of x is positive, negative, and 0. Again, we have to kind of observe these things graphically at this point because we don't know how to do derivatives analytically. So x is less than 3, and then we have negative 3/4 x for x is greater than 3. Okay, so that's my function. We're looking for any points where the function is not differentiable. So graphically, 1/3 x squared is going to be a parabola with a vertex of 0, 0, and it's going to open up, and it's going to be kind of wide. It's going to be kind of wide here because it's got a 1/3 a value, okay? And I'm just going to plug in a value of 3 to figure out what that point is, that limit is. 3 squared is 9, 1/3 of that is 3. So at 3, we have a height of 3 if it existed there, but it's an open circle. So this is generally the graph of our parabola. Then we have a negative 3/4 x, so we know it has a y-intercept of 0 and a slope of negative 3 over 4. So we'll say that's negative 3 over 4. And so we have this line that looks like this, but we're only looking for the values when x is greater than 3. So again, we have an open, circle here, and then we have a line. So where is this function not differentiable? Well, this part of the graph looks smooth, and it doesn't go vertical because it's a parabola, so it's differentiable for all values within this interval. And since that's linear, it's differentiable there because it's locally linear if it's a linear function anyways. So we'd say it's differentiable everywhere except when x equals 3. So we're going to say not differentiable when x equals 3 since h of x is not continuous when x equals 3. Okay, so that's it's not differentiable there. And then we can also say that it's a jump discontinuity, just to add a little bit more to that. The next part of this says determine where f prime of x is positive, negative, and 0. Remember, well, I got a typo there. It should say when h prime of x is positive, negative, or 0. So how do I know when the derivative is positive? Well, remember, the derivative means the slope. If the slope is positive, that means our function's going to be increasing. If our slope is negative, then our function's going to be decreasing. And if our function has a derivative that is 0, that means the tangent line is flat. In other words, we're going to have a horizontal tangent line. And so we can see where are we decreasing. We could say that h prime is negative. H prime is negative when h is decreasing. Therefore, where is it decreasing? It's decreasing here, so we would say from negative infinity, less than x, less than or equal to 0, and from 3, less than x, less than infinity. Now, the types of inequalities I use here, I'm not going to go into great detail, but this is not equal to because the function just doesn't exist there. This is equal to because of the definition of increasing and decreasing, and we'll get more into that in the future. H prime of x, actually I guess I could put that there because technically h prime is going to be 0 there. So h prime is positive. Again, we'll talk more about that in the future. H prime is positive when h is increasing. And so therefore that would be from 0, less than x, less than 3. Okay? And the last part is when is h prime 0? Well, h prime of x is equal to 0 whenever we can draw a tangent line that is flat, because then that slope would be 0. Well, we can see that we have a tangent line here that would be flat. And so we can say h prime of x equals 0 when x equals 0, since we have a horizontal tangent line. So a lot of different things going on today. We got on the computer and showed a different look of the idea of local linearity. We talked about the different types of non-differentiability, whether it be a corner, a cusp, a vertical tangent, or a discontinuity. Please pay close attention to those definitions and how to interpret what type of non-differentiability we have, because those are very important questions that pop up, and then of course the justification that goes along with that. Just like always, if you have any questions for me, please feel free to comment in the comments below or reach out to me and I'd be glad to help you out. Otherwise, have a great evening and I will see you next time.